All right. So here we have two spheres, 1 kilogram release from rest. And I thought I changed this one, but I guess not. So we're just going to work through it just to be safe. So we want the ratio of EGB to EGA in the picture shown. So that means the ratio is going to be MGH of B divided by MGH of A. Now the interesting thing, so this is actually how I'm solving this, is by taking these ratios like this. A little bit different than I might have done it before. So I'm just taking the ratio to start with, and if you notice, I actually have some letters that cancel even before we begin, so it turns out the ratio is just that of the heights. So HB is 20, HA is 10, and that gives me a ratio of 2 to 1. Now let's get the ratio of heights that they're released at. Now here it's not going to be 2 to 1 because I actually have to worry about the conservation of energy, and let's be clear. So the energy of ball B is actually equal to two things. There is the gravity component, and there is the kinetic energy component. So when I actually calculate EB, I'm going to end up getting 1 times 10 times its height, which is 20, plus 1/2 times its mass, which is 1. And V squared is 25. So I'm going to end up getting EB actually equals 212.5 joules. And I need to do a similar calculation. So I'll call this B, and this is B. I'm going to need to do a similar calculation for A. So the energy of A is going to end up being same thing. MGH plus 1/2 MV squared. And that means M is 1, G is 10, and the H ends up being 10 plus 1/2 times 1 times 36. This ends up being 118 joules worth of energy. So when we actually get the ratio here of energies, let's be clear. This is the total energy that we have. So let's be totally clear on this. It's the total energy. So when we're at our maximum height, we only have gravitational energy for B equal to 212.5 joules. And same with A. Its gravitational energy to start off with is 118 joules. And that's going to equal MGHB. This is going to equal MGH of A. And when we get these ratios, we notice that these cancel. And so this is actually the fraction that we get. We could simplify this if we wanted. And if we did, we'd end up getting about 1.8 to 1. Now for number 6. I actually managed to correct some of the physics on this, so we're going to actually do 6, 7, and 8 on this. So let's actually sketch our energy bar graph. So we begin with all gravitational energy at position A. And at B, we've got some gravity and some kinetic. Probably a better way to write this is that I've probably got more kinetic than gravity. So yeah, some kinetic, mostly kinetic, some gravity. At C, we have all kinetic energy. And then at D, we're going to have a combination of gravitational and elastic energy. So the amount of energy at point B, we want the kinetic energy at point B. So what we're going to do is we're going to actually set up our equation. So we have EG at A, using the bar graph, equals EG at B. plus EK at B. And now I can put in some numbers. So using this idea here, sorry, this is EK, not E alpha. So we're going to have 100 kilogram car, so mgh at A equals mgh at B plus 1/2 mv squared. So this is my energy equation. And now I can put in my numbers. 100 times 10 times HA, which is 30, minus equals 100 times 10 times 10 plus, now they want the kinetic energy, so I wrote 1/2 mv squared here, but I'm going to rewrite it as EK since that's what we're solving for. When we actually do solve for EK, just so you know, we're going to end up getting 20,000 joules of energy. And we want to know how fast the car is moving at point C. So we have mgha here gets entirely converted into kinetic energy at point C. I can actually cancel the m's here, and I'll get 10 times 30 equals 1/2 times Vc squared, or 600 is Vc squared, so Vc ends up being 24.5 meters per second. Oops. So that's it for the second page of the exam.